Amita, for a great first half of the course. I'm going to give the next half of the course, and it'll be slightly different. I got my hair cut yesterday, though, so now it's like the same length as Meta, so hopefully that'll ease the transition, but the topics might be a bit different. But the thing that is going to stay the same is the general theme that we're trying to get you guys all up to speed to prepare you for the upcoming courses. So the relevant courses would be the quantum field theory courses, the quantum information courses, quantum foundations, relativistic quantum information, a little bit of condensed matter. So there's some quantum theory behind condensed matter, maybe some statistical mechanics. And so the way that we've been doing that is by looking at things that you will be covering in kind of more complicated ways in upcoming courses, but doing them in a slightly more gentle way. So that's kind of what I'm going to be doing for the next 2 days. So Thursday and Friday, I will mostly focus on quantum optics. So you can think of quantum optics as being like a non-relativistic approximation to quantum electrodynamics. It kind of sounds weird because light, of course, is relativistic. But in quantum optics, what we do is we're usually interested in describing real-world experiments, so things that typically we do in the lab. And in those situations, the matter that the light is interacting with is non-relativistic. It's usually just like sitting there. And so we can make, we don't have to worry about Lorentz invariance, and we can make all sorts of approximations that make things easier mathematically. But conceptually, there are a lot of similarities with things like that you will see in quantum field theory, so things like second quantization and field operators and so on. So I will start by quantizing the electromagnetic field, and I'll do this in this, hello? Oh my God. This is not okay.
Sorry about that.
Is it okay now? Okay, but is it louder?
Yes.
Okay, well, okay, let's go with it. Yeah, so I will start with quantizing the electromagnetic field in a quantum optics context, which is easier than what you will see later on. And then I will talk a little bit about some interesting states of the quantum harmonic oscillator. So these are states that you will see typically come up in quantum foundations and in quantum information. So it'll be good for you guys to see them now. And then at the end of this lecture, I will talk a little bit about something called parametric downconversion, which is a nonlinear optical process that has pretty much been the workhorse of all quantum optics experiments for the last 20 years. So I think it would be really interesting for you to actually see how a lot of these states are done in practice. And doing that will prepare you for what we'll do in tomorrow's lecture, where I will look at the interaction picture and time ordering in the context of the Dyson series. And so there I will give a couple of examples from quantum optics as well. So one reason for doing this is because some of you may have already seen interaction picture in the Dyson series, but the examples that I will use, I'm almost certain that you wouldn't have seen, so it should be interesting for you as well, even though you may have seen these things before. So the example I will use for the interaction picture is spontaneous emission of an atom, a two-level atom inside a cavity. So we can see how an excited atom can decay and emit a photon. And then in the context of time ordering, I will again come back to parametric downconversion, but I will treat it in a much more involved way than what we will see today. So there we'll be able to predict the joint spectral properties of photons that are created using this system. And then next week, we're just going to change gears completely. And I'm going to talk about quantum mechanics in a different way. So rather than thinking about quantum mechanics in terms of, what is the system that we're dealing with, what is the Hamiltonian, how do we specifically solve a particular problem, we're going to kind of abstract away everything and look at the more general structure of the theory. So there, I will start with kind of the, and we will do this in an operational context. So what that means is we're going to think about how an agent interacts with a specific experiment. So we will talk about things like how you can make a preparation and what transformation you're going to do on the system, and then what are going to be the statistics of a particular measurement that you can do. So conceptually, that's a really different way of thinking about it than probably you've been used to in your previous quantum mechanics courses. And so I will kind of like, as the days go along, we will build up in generality. So I will start with just the ideal postulates. So we will talk about pure states, unitary evolution, and projective measurements, which is stuff that you would have seen before probably, but we will still go through it so that we can set the scene for generalizing things. So then the next day, I will give a new set of postulates that are slightly more general than these ones, and I will motivate them using statistical mixtures. So there, the transformations will be motivated as statistical mixtures. Sorry, the density matrices will be motivated as statistical mixtures of pure states. The transformations will be statistical mixtures of unitary operators, and the measurements will be statistical mixtures of projectors. But then we'll see that that isn't actually the most general thing. We can do something more general by coupling our system to some sort of environment. And in order to discuss that, we first are going to take a bit of a diversion and talk about composite systems and entanglement. And then once we're all comfortable with entanglement, we'll have what we need to discuss the most general postulates, which are in the context of, it's called Church of the Larger Hilbert Space. So it's in the context of applying ideal postulates on a larger Hilbert space, but then only describing a subset of the system that you have access to. So we'll get to that. And actually, I mean, I said it's the most general axioms that we have, but I will discuss a few situations that still can't be described in terms of these axioms. And it's kind of an open area of research now, how to get these even more general descriptions. So that's the week ahead. And then finally, at the end, I thought we could have a bit of fun, and I will kind of go in a quantum information direction, and I will tell you a little bit about how to model quantum systems using quantum circuits. And then that will give you, I mean, all of this together, and the idea of quantum circuits will give you everything that you need to understand quantum teleportation. So I will go through the quantum teleportation protocol in detail, so then you can like tell your friends that you know how to do teleportation. Okay, so that is the week ahead. My board is almost dry. But before I start with quantizing the EM field, do you guys have any particular questions? Oh, okay, wait, questions? No? Okay, so, and I have a reminder to talk about the homework. So the homework is going to be mostly about everything that will be covered in these 4 lectures. So I will give you the homework tomorrow, and I suggest you read through it and maybe like highlight the things that, like the concepts that you're not familiar with. And then as we're going through the lectures, you can kind of keep an eye out for the things that you're going to need to do the homework. And then the homework will be due on the Thursday during the research and study week. So you'll have like almost 2 weeks to do it. Okay, good. So let's start with quantization. And I don't know how long this is going to take, but I would like to fit in a 5-minute break after the kind of like here. So if I forget, like just remind me that I wanted to do that. Okay, so in quantization of the electromagnetic field, sometimes this is known as second quantization. I'm sure you hear this every time, but it's good to, so everybody knows it's kind of a misnomer. There's nothing that's like being quantized a second time. first quantization is when you quantize the position and momentum. Here we're quantizing the field operators. But if you do see it, people talk about second quantization, that's what they're referring to. And so we're going to do this for a free electromagnetic field. So a nice place to start is the source-free Maxwell's equations. So I'm being lazy and not putting arrows and everything, but the fields are vector fields. And in order to progress, what we want to do, so these equations, they're gauge invariant. So we're going to have to pick a specific gauge in order to be able to solve things. And so what you're going to see is in quantum field theory, people are going to be really concerned with Lorentz invariance. And so you're going to, they're going to pick something called the Lorentz gauge. But here, like I said, we're doing quantum optics, so we don't really care about Lorentz invariance, and we want to make things as simple as possible. So we're going to pick something called the Coulomb gauge. So maybe I'll write that down. So in quantum field theory, you're going to see this. Oh, okay, so it's like two different Lorentzes. So the Lorentz without a T gauge is, but that ensures that you have Lorentz with the T invariance. But in quantum optics, we pick the Coulomb gauge. Which is that. Okay, and so from this we can determine expressions for the electric and magnetic fields. And then what we want to do is use Maxwell's equations in combination with the gauge to write down a wave equation for the vector potential. Now, because I don't want to spend the entire lectures going through the details of the derivations, I'm going to jump a few steps, but I've set these things as tutorial problems. So the step for how to get from here and using this condition to there is something that's going to be a tutorial problem tomorrow. So if it's not immediately obvious, don't worry, you'll figure out the details. And then the next step is to separate the solution for the vector potential in terms of the positive and negative frequency components. Okay, so we're going to, so the way Dirac originally did this, he quantized the electric fields, but we're going to work with the vector potential, which is the way they do it in quantum field theory. And then from that, once we quantize that, we're going to extract the expressions for the electric and magnetic fields. Okay, so at this stage, we have this expression in terms of the positive and negative components. And what we would like to do is write it out in terms of the Fourier components of each of the fields. And it's always, yes?
Did we set the electrostatic potential to 0? A scalar potential?
I don't think there's a condition on it.
Well, it's missing from the definition
yeah.
of the electric field.
Oh, sorry. Yeah. So there's no sources. So there's no potential.
Well, there's.
But we can set it to 0 anyways.
Okay, we can set it to 0.
Okay.
Just asking if we have.
Yeah, I don't know. So let's go with yes, and then I can confirm. Yeah, in the next lecture.
We're in vacuum right now?
Sorry?
We're in vacuum right now?
We're in vacuum, yeah.
Is it part of the definition of Coulomb gauge to put it 0?
Yeah. I haven't seen the yeah, whenever we write down the Coulomb gauge, we just write it in terms of that. I don't, off the top of my head, remember what we do with the phi. But yeah, let's come back to it and move on at the moment, because I don't know the answer off the top of my head. Okay, so we want to write out the vector potential in terms of the Fourier components. And it's always easier to deal with discrete components rather than continuous ones. So we're going to assume that we have some sort of volume, and we're going to quantize within that volume. Ultimately, what you can do is send that the size of that volume to 0, but to infinity, but we're not going to be doing that here. Okay, so now we can expand the vector potential in terms of orthogonal mode functions. And I'll just write down the positive frequency component or negative frequency component. And so usually you specify the explicit form of this function, and it's going to depend on the volume that you're choosing. But here we're going to keep it general and just work with the general properties of these mode functions. So let's write down some properties. So the mode functions themselves satisfy the wave equation. And the transversality condition. And they also form a orthonormal set. Yeah,
Can you write bigger, please?
bigger. Okay.
Yeah, I'm wondering if not the light or something.
Is it reflecting badly? Yeah, but okay. Do you want me to rewrite anything in particular before I continue on?
I just want to know what those functions of the orthogonal what function?
Oh, mode. Okay, that's probably just my bad writing, not the size. I'll try and be less sloppy. I don't know if that helps. Mode. Mode. Yep. Okay, and now I'm just going to rewrite. This is like just a matter of convenience to make the factors come out right at the end, but I'm going to rewrite these CKs in a slightly different way. Okay, so here we still have a complex number, and I've just pulled out a bunch of factors so that we get the answer that we want. And now using this expression for the fields in terms of the vector potential, we can rewrite the EM fields. Okay, so now the quantization procedure, which is mysterious and part of Dirac's genius, is that we now take these complex numbers and elevate them to being operators that satisfy bosonic commutation relations, because the photons are bosons. So in doing so, typically people put hats. But since we'll be dealing with these operators over and over again, I'm not going to write the hats. But I will change this to being Hermitian conjugates and specify the bosonic commutation relations. Yes.
Okay, so I have three small questions. The
Sure.
first one is, these things are vectors, so what's their direction?
Yeah, so the direction is, it's all of that will be inside the mode function. So they will have these things that they will be like, I just didn't really want to specify them. And then they have a polarization component as well. And then you're summing over like all of the directions and all of the polarization components.
Okay. The next one was, you have an orthogonality relation, and these are radials. So do we have some sort of real Jacobian? Is it just against? Are we just integrating against the R, or we?
Oh shoot! Sorry. Good. And over the volume. Does that help?
I guess. And then the last one is, are we using like complex fields or something, because the fourth Maxwell equation has got an extra minus?
If the Maxwell equation is wrong, it's probably a typo. Yeah.
So the I's are just to get rid of phase and do something else. The ones when we actually come to the end, those are different. Those are just I's. Just
the I's that are here, you mean?
yeah.
Yeah, they are so that we get the answer that we want at the end. Yeah, does someone want to cross-check the Maxwell equations if you have Google? And I can see the fourth one. It should be a plus.
It's plus.
Thank you very much for that. Okay, so we've elevated the complex numbers to operators, and now the last final step is to, which is going to be something you guys are going to go through the details in your tutorial as well. But what we're going to do is, maybe I'll write it down. Okay, maybe I won't use the presets on that one anymore. This board is always playing up, really frustrating. Yeah, so what we want to do ultimately is to get to the point where we can write down the Hamiltonian in terms of these operators that we've just created. So we start with the Hamiltonian for the electromagnetic field that we just get from the expression for the energy, the classical energy. So we have H is equal to half integral over R, and then in terms of the electric and magnetic fields. Okay, and so the thing that you guys are going to do in your tutorial is to show that if we take these quantized expressions for the magnetic and electric fields and put them in here, and then use a whole bunch of relations, so the orthonormality relations, and then some other expressions that I will give you, as well as some known vector identities, and so on. You can go through in a few steps and show that this is equal to the sum over k, h bar omega k, a dagger a plus a half. So does anyone, yes?
Are we supposed to use some sort of complex conjugation while defining h, like e star e or something like that? Because we use the exponential.
Sorry, let's go back. Some sort of complex.
These e squares and b squares appearing in h.
Yeah, I don't think.
Some sort of e star times e.
I don't think so.
Or just this.
I don't think they're supposed to be. Maybe they are. Let me cross-check that again. So I initially had I had it like this, and then I convinced myself that it shouldn't be there when I was going through the details of your tutorial tomorrow. But I think I can see why you would want them to be there.
The real part of.
No, they're not the real part there. Yeah. So okay. Oh yes, it is real, because yeah. Sometimes it's really hard to think when you're up here on the spot, so I will always blame it on that. But these things are complex, but the electric fields are real when you add both of the when you add the two complex parts, the sines cancel or the cosines cancel, and you're left with a real field. Yep. But we can totally confirm this and make sure that it's correct when we're going through the tutorial. Okay. So yeah, as I was saying, does anyone recognize this expression at the end? What is that? What is that? Oh my God. Okay. That is a set of uncoupled harmonic oscillators. So it's cool. It means that we can treat the electromagnetic field as a set of uncoupled harmonic oscillators, which we love because harmonic oscillators are easy to deal with. So if you did the last question of the tutorial, you would have seen that actually, let's not talk about that yet. What do I want to say? Yeah, so then the quantum states of the electromagnetic field, they can be just described as tensor products of states in each of the modes. So that makes our life easier when we do calculations. Okay, and so the other thing I wanted to point out is that this operator here, it's sometimes known as the number operator. And this component here represents the vacuum energy of the field. So, okay, how are we going? Okay, so this took a little less than I expected. So I don't know if you guys actually want to have a break at this point, or do we want to just keep going and move the break to the end of the lecture? Put your hand up if you want a break. No, everybody's loving this so much they want to keep going. Okay, so what have we shown? We've shown that we can think about the electromagnetic field as a set of uncoupled harmonic oscillators. And now the next thing that I wanted to do was go through the properties of some interesting quantum optics states that we deal with. So why would we be interested in making states of light that have quantum properties? One of them is if we're trying to maybe do some sort of quantum information related tasks. Like if we want to send quantum information from one place to another, then we would want to encode that information in a quantum system, and light is the best system in order to send information from one point to another. So if you want to do some sort of quantum cryptography task or quantum communication, if you want to do maybe if you have like a quantum computer, probably it's not going to be built out of light, but different modules of the quantum computer might be linked with light, so you might want to do it for that. Quantum optics has also been the test bed for doing quantum foundations experiments. So the Bell experiments that Rob mentioned in his talk at the beginning of this course. So they're really important experiments that gave us some more information about the nature of reality. So those were done with quantum optics, quantum light. And also there's different types of measurements that you might be able to do that are enhanced with quantum light. So for example, the gravitational wave experiments, they were done using classical light in the interferometer, but you can actually enhance the precision of those experiments by putting in a specific type of quantum light. So I will talk about all of those different lights in the next part of the lecture. Okay. Okay, so if you were giving this lecture, what would be the first state of light that you would start with if you, let's say, had this Hamiltonian?
Just 1K?
Just 1K. 1K, you know, I'm like totally even just assuming that. But yes, yes, I'm very good. That's just an assumption I like made implicitly. So good. Pardon me?
Ground state?
Ground state. Ground state is a good state, yeah. So what you might do is figure out what the ground state is of this Hamiltonian. You might just try and find the eigenstates of that Hamiltonian to maybe make it a little bit more complicated. But I mean, typically with Hamiltonians, first thing you might want to try is diagonalizing it. So what we can do is to do that and write down the eigenstates of this Hamiltonian. And it turns out that the eigenstates, they correspond to the number of photons inside, the number of excitations of the field, which we can interpret as photons. So this Hamiltonian, it has eigenvectors I think I wrote something confusing here, but anyway. So these are eigenstates of the Hamiltonian, and they're also eigenstates of the number operator. So if we act the number operator on this eigenstate, we get out the number of photons in that state. And as we mentioned before, there is a ground state, which is defined by A acting on the state, gives you 0. And as I said earlier, the energy of the ground state is h bar omega, and then if we want to know the energy of the whole thing, sum over h bar omega k. Okay, so you guys would have seen these operators with Meta, and in the context of, let's say, a harmonic oscillator that maybe is a single particle in some sort of harmonic potential, then these operators take you up and down the ladders of the the harmonic oscillator. And so they're called lowering and raising operators. But here, because we're interpreting these as excitations of the field, we typically call them creation or annihilation operators. But the mathematics, and mathematically, these operators are the same as the ones that you saw before. So what happens when we act these operators on the number states? Okay, maybe let's do some terminology. Okay, so yeah, these things, I've been calling them number states, but they're also sometimes called Fock states. And those terms are used interchangeably. Sometimes, so you'd be surprised how immature senior researchers can be, but they can be pretty immature. And so sometimes people have fun with that. Okay. Especially when you're writing a paper and you've been writing it for a really, really long time, and everybody kind of is just going a little bit crazy, and they start doing plays on words on the titles of the manuscripts and stuff. Anyway, okay, where were we? So we can act these operators on the number states, and they do the following. So acting A on the number state reduces the state by the number of photons by 1, and then we get this coefficient out the front. And then if we act the creation operator, then as you'd expect, it's going to increase the number of photons by 1. And we also get this coefficient out the front. And you can also think about how would we, if we started off with the vacuum, how would we create an n photon state? Well, we could apply the creation operator over and over and over again. So if we have repeated application, so if we apply a dagger on the vacuum state, then we get the n photon state. So that all makes sense intuitively. Okay, and now I've been dropping the k's because I said that that I'm assuming that we only have a single mode, but we can consider having multiple modes and think about the relationships between the Fock states in and for different k's. So we can say that the number states are orthogonal and complete. Oh, okay, hang on. Maybe don't worry about what I just said about the k vectors. So if you have two of the same states with the same photon number, they're going to have overlap 1, but if they're different numbers, then they have 0 overlap. And also they form a complete set of basis vectors. So there's a completeness relation like this. And this is a good point for me to point out that sometimes I get sloppy when I'm writing things. And so you'll see people do this a lot who work with density matrices or projectors. So rather than writing this, sometimes people write an X between like that. It's just faster. But I went through a whole lecture once doing this, and then at the end someone's like, yeah, but what are all of those X's? so I just want to make it clear. Sometimes when I do that, that's just a simple, a faster way of writing the outer product. Yes?
Are we working with a cutoff or are we summing over all Ks?
Summing over all Ks, yes. Yes. So the Ks, you mean like a cutoff at the top?
Yeah.
Or,
Is there a maximum? K is like a natural number?
K is a funny index which captures the sum over the polarizations, so the two polarizations, and also over all of the modes inside the volume. So for the modes, there is no cutoff. I think they can get like, well, there's an infinite number of modes.
Well, then that, like the energy of the ground state is gonna be divergent, right?
Yeah. So in practice, in quantum optics, this doesn't become a problem because we're usually dealing with optical fields. So we don't deal with high energy stuff. I expect that there are some subtleties there, and that's stuff that like Dan and Gang will talk about in quantum field theory, so I'm going to divert to them. In the context of applying things to quantum optics problems, it's not going to be a problem. I understand that that's not very satisfying, but I will just divert that question to those guys. And you don't have to wait for the course. You can also just go knock on their door and say, hey, can you explain this thing? Okay, so far we've been talking about number states, and these are nice states for situations when you're dealing with small numbers of photons, like maybe in quantum field theory, maybe two particles annihilate each other and create a photon or two photons. But in quantum optics, typically we're dealing with large fields, so things like states that come out of a laser, maybe. And so in that case, there are different types of states that are more natural to describe quantum optics problems rather than these Fock states. Although, I mean, the Fock states, they definitely play a huge part in quantum optics, but there are some other states that are more natural. So one of them is called the coherent state, which I think, did you guys see it on yesterday's tutorial? Yeah, you guys were doing some displacement operators. Yeah. Okay, so the coherent states, they are not eigenstates of the Hamiltonian, but they are actually eigenstates of the annihilation operator. So that's another thing that you guys are going to show in the tutorial. And so we'll see later why it's nice to have states that are eigenstates of the annihilation operator, because it lets us make a connection between the quantum description of these states and also classical descriptions of electromagnetic fields. But let's first define these states and discuss some of their properties. So a nice way, as you saw in the tutorial yesterday, a nice way of defining the states is in terms of a unitary displacement operator. So then the coherent state alpha, where alpha is a complex number, is going to be defined as the displacement operator acting on the vacuum. And so the reason it's called the displacement operator, which is something I'm not going to go into in very much detail, but you can think about, so since these things are harmonic oscillators, you can think about them in phase space. And so you can actually draw different phase space distributions, phase space distributions that correspond to different states of the EM field. And so typically what they've done is they're drawn in terms of these things called quadratures, which are they're analogous to position and momentum when you're dealing with some sort of particle. And so in these phase space diagrams, typically a vacuum state is in the middle and it has some sort of quantum uncertainty. And then what the displacement operator does is it displaces the state from the middle to some point in phase space, where then this line is given by the magnitude of alpha, and this phase is given by the arg of alpha. So that's just to explain a little bit of the terminology. And so as you will show in the tutorial, or maybe, I don't know if you guys already showed this, but the coherent state is eigenstate of the annihilation operator with eigenvalue alpha. And we can also expand the state in the number basis. So what we find is that it's a sum from 0 to infinity over n. And so looking at this state, you can see that it's actually a state of indefinite photon number. So with the Fock states, we had a state, of like 5 photons or 6 photons. But here it's this state of some distribution over the photon numbers. And so it turns out that this type of state is actually a very good model for the state of light that comes out of a laser. So in that type of light, we actually can't say how many photons there are in this laser. We can only talk about things like expectation values and look at the distribution. So if we wanted to plot the photon number distribution of a coherent state, it would be something that has like a Poissonian distribution. And then this distribution is going to be centered around the expectation value of n. So what else can we say? Well, we can calculate the overlap between two different coherent states. And what we find is that the states are not orthogonal. So if we have two states, beta and alpha, then there will be some sort of overlap. And it's going to depend on alpha and beta. So let's say I have my state alpha in phase space here, and let's say some other state beta. So in these phase space distributions, the coherent states are typically represented as Gaussian states. So there's going to be tails that overlap between the two coherent states. So there'll always be some non-zero overlap, but as the states get further away in phase space, then the overlap is going to get really small. And so I think for alpha is equal to 2, then this overlap, well, is it's really, really small. So even for average number of photons too, the overlap is small. So these states are not orthogonal, but they actually form an overcomplete basis. So we can write down another completeness or overcompleteness relation. so what's nice is that since they form a basis, we can, yes?
Did you say that's a Poisson distribution?
Yes.
Sorry.
Yes.
Are we missing an nth power in the expansion of alpha?
Yes. Are we? That should not even be an alpha. Oh, hang on. Yeah.
Power.
Yes. Very good. Okay, and actually something I didn't say. So the thing that's interesting about the coherent states is that so I said that they have a uncertain number of photons, but they actually have a pretty well-defined phase. So we can, as I drew in that phase diagram, even though there's some uncertainty in like the distribution, there's something like a well-defined phase. While the number states, on the other hand, they have a well-defined photon number, but they actually have no notion of phase at all. So if you were to draw them, maybe I can draw it here. If you were to draw the number states in phase space, then you get kind of these concentric rings that can go negative. So if you look at them, they kind of like have all of these ripples, and there's more ripples the higher the photon number is. So we have something that has a well-defined number of photons, but a indefinite phase. And then here on the other end, we have something that has a pretty well-defined phase, but an indefinite number of photons. But as I was saying, so these the coherent states form a basis, so we can actually take any quantum state, regardless of how complicated it is, and write it in the coherent state basis. And then when we do calculations, we can exploit this fact that the coherent state is an eigenstate of the annihilation operator, and that can make our life pretty easy. And so the final thing I wanted to say about the coherent state is we can make a connection between the quantum description of light and the classical description. So maybe I'll do it down here. So, like, the funny thing about the different types of language that you use in different communities, it like sometimes becomes a problem when you have classical optics people talking to quantum optics people. So in classical optics, when people say a field, they say there is a field, they mean that there is some presence of light. While in quantum optics, the field is an operator which kind of describes the structure of the system. But when we talk about the presence or absence of light, we talk about the states. And so the way that we make a connection between these two is to take, if we want to know what the classical field is, we take the expectation value of the field operator to get the, with respect to that particular state of light. So for the coherent state, you would sandwich it in between the electric field operator. And so you can see, let's see, where is it? Okay, it's over there. So if I sandwich that object between the alphas, they're pretty much just going to move through everything because everything is a number until they get to this creation or annihilation operators. And so you'll have the annihilation operator acting on the coherent state from one side. Or the other time you'll have a creation operator, but you can just pretend it's an annihilation operator in the other direction. And so you'll essentially get something that looks just like that, but with the creation and annihilation operators replaced by alphas and alpha stars. So you'll get something that has the form which hopefully looks to you like a classical field. So, and I mean, like, depending on what the form is here, if this is something like, e to the I k dot r, then you'll have the complex parts cancel, and like roughly it'll become something like sine of omega kt minus k dot r. So I'm being like very hand wavy here, but you can kind of imagine that like if you work through it carefully, you'll get something that looks like that. So it really is, the classical field. But I think you'll show, one of the tutorial questions is you'll see what happens if you take a box state and try and calculate the expectation value of the electric field operator, and you'll find that you get 0, which is kind of interesting, and you can think about what that means, like that photons have no electric field. I don't know. So, okay. Okay, so far I was talking about coherent states, and I was drawing them in phase space. And so coherent states are what are known as minimum uncertainty states. So that means that they satisfy an uncertainty relation. They saturate an uncertainty relation between the uncertainty in one quadrature and the other quadrature. But there's actually a whole class of minimum uncertainty states called squeeze states. So those are states that have reduced uncertainty in one quadrature below the quantum noise limit, but at the expense of having increased uncertainty in the other quadrature. So to make that a little bit more precise, what I'm going to do is I will write, I'll decompose the creation operator in terms of these quadratures that I was talking about. And then these things satisfy their own commutation relations. And they satisfy this uncertainty relation. Okay, so with coherent states, we have that the uncertainty in x is equal to the uncertainty, in x1 is equal to the uncertainty in x2, which is equal to 1. So we get this nice Gaussian. But with squeeze states, we can have something that looks like this. So that will give us delta x1 and delta x2. So they still saturate this uncertainty relation, but they don't do it in a way that the widths are the same in both quadratures. So just to compare, that would be a coherent state. Okay, so we can define these squeeze states in terms of a squeezing operator. So before we were talking about a displacement operator. Here we can define an operator that squeezes a state. And actually, I'm only talking about squeezed vacuum states here. So let me redraw this picture. Okay, and so we want to define them in terms of the squeezing operator. Okay. So the squeezing operator kind of looks like the displacement operator, except you can see that it has squared. The operator's squared. Epsilon here is a complex number, so the magnitude of epsilon determines how much squeezing there is, and the phase of epsilon determines the axis on which you're doing the squeezing. And so this is the state of light that's actually being proposed to be put into the next stage of LIGO, which is the gravity wave interferometer. So there, what they have is this huge Michelson interferometer, which looks something like this. I mean, but these things are like kilometers long, these arms. So they put in, well, laser light, and in here, usually it's a vacuum state, and then the light goes in. You know, some of it reflects off the beam splitter, some goes through, then like hits a mirror, reflects back, and there's some sort of interference going on. And I think they have it set up so that it's like the phases cancel out properly, and then if a graviton or some gravity wave goes through, then it like perturbs it, and then you can detect some amplitude out of one of the modes. And so this thing is limited by, well, a number of things, but one of the things it's limited by is this quantum noise. And so the proposal is that now, instead of putting in a vacuum state into this mode, they can put in a squeeze state, and then hopefully that should improve the sensitivity of the interferometer. Okay, so then just briefly, the last type of state I wanted to tell you about is called a Schrödinger cat state. So you guys are probably familiar with the Schrödinger cat paradox. So the analogy here, so in the Schrödinger cat experiment, you start with some reasonable assumptions, and then eventually you get to this like absurd conclusion that you have a live cat and a dead cat in a superposition. And so the analogy here is that the alive cat and dead cat are two macroscopically distinct states. So since the coherent state is a state of a laser, which you can think of as being like the most classical quantum state, then if you can take a superposition of two really large coherent states with different phases, then that's like an analog of a Schrödinger cat state. So, so let's say optical Schrödinger cat state. So there's, I mean, you can generalize these cat states, but there's like two main ones that people talk about. So one is called the even cat state, which is a superposition of alpha plus minus alpha with some normalization. And the other one is a superposition of alpha minus alpha. Okay. So does anyone want to take a stab at why they're called odd and even cat state? Maybe like take a look at some other stuff on the board.
First one's even with respect to alpha.
Pardon me?
Alpha goes to minus alpha.
So both of them have alpha and minus alpha.
So first one's even, and with respect to alpha goes to minus.
Oh, okay. So like you think that the parity is even? Yeah. That's, you know, that's a good interpretation. It's not actually the reason, but I like it. It's kind of a, yeah.
You can only has even and.
Pardon me?
You can only has even and.
Yeah. Yeah. So if you take a look at, where do I have? Okay, if you look at the photon number distribution or photon number representation of the coherent state, you see that the alpha sits in front of the n. So for the minus alpha, you'll have a minus sign in front of the n's for the odd n states, but you'll have a plus sign for the even n states. So when you add these two things together, in this case, all of the odd n's are going to cancel each other out, and you're going to get something that's a superposition of just the even photon number states. And here you will have something that is a superposition of just the odd photon number states with like appropriate coefficients. So that's why they call them even and odd states, even and odd cat states. And so these things, they're interesting, I guess, because they're cute. But you can also show that you can use them as a basis for encoding quantum information. So these states, the even and odd cat state, are orthogonal, so they can form a qubit. And there is an alternate method for doing quantum computation just with these cat states rather than with polarizations of photons and so on. Yeah, and they're also interesting because they're really susceptible to decoherence. Like it's really, really hard to make states that are coherent superposition of large photon number states. So we'll talk a little bit more about decoherence in upcoming lectures. But there are proposals for maybe using these types of states to detect interactions with really like weakly interacting states of matter. Okay, so these are pretty much like the four most talked about states in quantum optics, and they've got they're useful, they're interesting from a kind of fundamental perspective, but they also have practical applications. And in the last part of the lecture, I just want to tell you a little bit about parametric downconversion. Yes?
How do you compare squeezed states?
Aha, I am just about to tell you. Yeah, so I want to tell you about parametric downconversion, which is the way that we prepare squeeze states and other interesting states of light. So today I'm just going to kind of give a cartoon overview of this process. But tomorrow, once we get into looking at time ordering, we're going to like really get into the nitty-gritties of how to model this thing. So we will start with an actual Hamiltonian and like go through everything and see how it's made. So, but here I will kind of give a cartoon description. So parametric downconversion is a nonlinear process. Nonlinear optical process, and the process is mediated by something known as a nonlinear crystal, and in particular, it's something called a second-order nonlinearity. So I will explain tomorrow what I mean by a second-order nonlinearity, or maybe I can whatever I can explain now. So okay, you can. Like you can think about this crystal as having a bunch of atoms with like electrons. And when you apply an external electric field, then it induces a nonlinear polarization in this material. So you kind of get this, like the electrons move away from the nuclei, and they kind of form an effective polarization, which then can generate new fields. And so this polarization is typically can be expanded in like a nonlinear way. So you get like a linear interaction, a nonlinear interaction, and then like so on. And so this interaction is like what happens, glass. If you have light just going through the window, you get one input field and one output field, and everything's like at the same frequency. So you can think of this as, it's called two-wave mixing. Then the second order nonlinearity, you can put in one field and get two fields out, where it satisfies momentum and energy conservation. So it's an interaction between three fields, and it's called three-wave mixing. And then at the next order, you can put in one field and get three fields out, or put in two fields and get two fields out. So it's an interaction between three fields. But parametric down conversion just deals with three interacting fields. So, okay. So let's not worry about the underlying physics for now. And so typically in a parametric down conversion setup, you put in one classical field at frequency omega p, so p stands for pump, and then you get out two fields, let's say at frequency omega a and omega b, and then also like the original field comes out, but we don't really model it. And it satisfies energy conservation. And this is a spontaneous process. So typically this thing coming in here, it's like a laser, and it has loads of photons. And occasionally, spontaneously, one pair of photons gets split into two pairs of photons. One photon gets split into two pairs of photons. So you might imagine that the state that describes this state of light would be something like one photon in mode A and one photon in mode B, but it's not, because like I said, it's a spontaneous process. So sometimes you get 0 photons in mode A and 0 photons in mode B. So you can like put some coefficients out the front, where these coefficients, they depend on how many of these, how strong this interaction is. So if the natural nonlinearity of the material was higher, then this coefficient in front of the ones is going to be higher. If the intensity of the pump is higher, then this coefficient will be higher. So you get a state that looks like that. But sometimes it's possible that like 2 photons from the pump split up into 4 photons. So we also get another contribution, which is something like this. And then you also have the higher order processes. So this thing just like goes on forever. Okay, so it turns out that this thing is what's known as a 2-mode squeeze state. So it's 2 modes because we have 2 different frequencies coming out here. And typically, experimentally, these things are also 2 different polarizations so that you can split them apart. But you can set things up experimentally that these 2 things come out at the same polarization and the same frequency. And then what you actually get out is something that's called a single mode squeeze state, which looks like this and so on. So it might not be obvious that that actually is a squeeze state, but if we look at the squeezing operator, you can kind of imagine that if you did like a Taylor expansion of this state, then you would have something that's like 1 acting on the vacuum, so you get a vacuum turn. Then you get something that creates 2 photons, so you get this like 2 photon term. Then you get something that's like the product of that, so it creates 4 photons. Or it creates 2 photons and then destroys 2 photons, so you get like a correction to the vacuum term. So if you acted the squeezing operator and then expanded it out in the photon number basis, you would get something like this. Okay, So what do I want to say about down conversion? So one thing you can do is set up your experiment in like what's called a post-selective way, that you like you're putting, let's say you're putting this entire state into your experiment, but at the end you have photon counting detectors that post-select on the situations where you only had like 2 photons. And so those are the type of states that are used in the Bell experiments. So they can actually they can set these things up so that you have 2 photons coming out, but they're entangled in polarization. And then they like send them to different parts of like the building. And then they have photon detectors that only post-select on the situations where you like get 1 photon here and 1 photon there. And then they do these Bell experiments. So you can use it as a source of entangled photons. So maybe we can say that. So that's like nice, but we don't really, I mean, okay, that's fine if you're doing some sort of like foundational experiment or some sort of proof of principle experiment, but sometimes you don't want to do like a post-selection thing. You want to actually like have a state of light that you know that you have and you can send it. So this kind of becomes problematic with down conversion because it's a spontaneous process, but you can kind of make up for it by using a process known as heralding. So what that means is you put a single photon detector here and then wait until that detector goes click. So when that detector goes click, it tells you I have a single photon here. So it means that your state actually corresponds to this term, and you know that you have a single photon in this mode. And then when that detector goes click, you can say, okay, now I can send my photon, to some satellite and like send quantum information. So it can be used as a heralded source of single photons. So heralded is kind of like, heralding is announcing that something has happened. As I said before, you can set things up in a way that what comes out is a squeeze state. And so the squeeze state itself, it's what's known as a Gaussian state. So like even though it's got these advantages that you can do enhanced detection with it, it's not really considered a quantum state because these quasi-probability distributions that I was talking about, for a squeeze state, it doesn't go negative, and typically the one way that people decide whether a state is quantum is whether this quasi-probability distribution goes negative or not. So they kind of like not really like quantum states, but they are. But with that caveat, can you kind of see any connection between this state and the cat states that we were talking about? Yeah. Right, the photon number distribution. So you can calculate the overlap between this squeezed vacuum state and the even cat state. And it's okay, it's not that high, but it's not bad. But it turns out that if you start subtracting photons from these guys, then you get a closer and closer approximation to a cat state. So if you act the annihilation operator on this state, then you would get something that's like, I don't know, some coefficient, well, that'll disappear. You get some coefficient 1 plus another coefficient 3, and so on. And this thing has a quasi-probability distribution that goes negative, and so it's more a quantum state, and it actually has a pretty good overlap with the cat state for small amplitudes. So they're called Schrödinger kitten states because they're small. But then you can like subtract another photon from it and get an even better approximation to an even cat state, and you can kind of like we'll see where that's going. But nobody wants to like subtract multiple single photons. So there are kind of more sophisticated schemes where you do some type of post-selective measurement on these things and get better and better approximations to these cat states. So we can call it Schrodinger kitten states. Okay, so it's a pretty versatile source of light. It's really cool. Just to say a little bit about how you subtract photons. So, okay, let's imagine we've got our single mode squeeze state coming out of here. What you do is you put a really weakly reflecting beam splitter here. So like, let's say reflectivity equals like 0.0001 or something. And then you put another photon detector here. And you just wait, and when that detector goes click, then you know you've subtracted a photon from this mode, and then what comes out here is like a kitten. Or you could, wait for this to be like a 2-photon click and get a better approximation. Okay, so I think that's kind of all I wanted to say. Just to preempt what we will be doing tomorrow, when we talk about time ordering, what I'm going to do is treat this in a lot more detail. Here I've been kind of pretending that this is a single frequency coming in and that we have single frequencies coming out of the other side. In practice, this will have some sort of spectral distribution. This will behave really differently at different frequencies. And what comes out here is going to be entangled in frequency. So you have to actually describe the state that comes out as a distribution, like a joint distribution over all of the frequency modes. And when you start looking at the higher order terms, that's where time ordering becomes important, because it really like changes the shape of the spectral correlations between the light. So we will do that tomorrow. So for this lecture, are there any questions at all? Okay, so we will see each other tomorrow, and I will talk about interaction picture and time ordering.